Hello everyone and welcome to MV Tutors. I'm Tolo and I thought I would make this quick video. I don't know if it's going to be quick. But yeah, I'm hoping it will be quick, but it's more to do with the graph questions that you might get for electric circuits. Okay, and before I begin, I just wanted to draw just a few graphs and just try to help you with interpreting what the graphs are about. So let's just say we have voltage here measured in volts, and we have current measured in amperes. By the way, please don't forget to like our videos and subscribe to our channel, and I hope this helps you as you prepare for your paper on Friday, particularly in the Gauteng province. Okay, so let's say we have a graph of voltage versus current. Okay, what kind of a relationship are we expecting? Well, we're expecting a positively linear function. Okay, and what would be the gradient of this function over here? Well, remember, gradient is delta y over delta x. Okay, and in this case, our delta y would be a delta v, our delta x would be a delta I. And looking at Ohm's law, remember Ohm's law is equal to V over I. Okay, your voltage over current. So in this case, your current is actually, your gradient. Your gradient is actually your resistance. Okay, so that is your voltage versus current graph. What if the current and the voltage were to be swapped? Okay, still gonna do the same thing. You have your current measured in amperes, voltage measured in volts, and you still have the same positively linear graph. Okay, and our gradient over there, let's just see, that will be delta I over delta V. So you'll see it's sort of like the inverse of what we had above there. So your gradient is actually 1 over R. Okay, 1 over R would be your I over your V. So the gradient is 1 over R. All right, so that is pretty much straightforward. Now, what if, I forgot to insert pages. Okay, what if we had EMF or potential difference? Okay, this time it's not just voltage as it is probably a terminal potential difference. Okay, remember with your equation for EMF, it is equal to your terminal potential difference, okay, plus your lost volts, right? Terminal potential difference, that would pretty much be your current in the circuit, and you would multiply that by your external resistance, and then your lost volts would be your current in the circuit multiplied by your internal resistance. Okay, so what if you were dealing then with terminal potential difference? So we're going to look at a scenario where you have terminal potential difference, right, measured in volts, and that would be against current. What would we expect then? All right, so in this case, please just bear in mind, in this scenario, you would have a negative linear function or relationship, linear graph. Okay, and in this case then, if you look at your EMF formula, okay, like I had said, it is equal to your terminal potential difference plus your lost volts. Okay, and if we were to write this in terms of your terminal potential difference, that would be equal to your EMF minus your lost volts. Let me just erase that. Okay. Minus your lost volts. Okay, and your lost volts, remember, that is basically your current times internal resistance. Now, I hope you see here that you have actually a negative, right? Do you see the relationship? You have a negative linear function, all right? And if we were to get the gradient, therefore, just actually think about this function being y is equal to mx plus c. Okay, if that were the case, this would be your y. Okay, EMF would be your c, and actually R would be your m, and then I would be your x. Why? Because I mean I is there on the x-axis, okay, and terminal potential difference is your y-axis. So that's why the R has to then be a gradient. So if you were to write this equation in the form that you know y is equal to mx plus c, it would be terminal potential difference, which is equal to R times I, that is negative, and then plus C, which is your EMF. All right, so on your graph, your y-axis, that is your EMF, okay? And then your gradient would just be negative R, okay, which is your internal resistance. All right, or let's just say R, your internal resistance. Okay, by the fact that it's going down from left to right, you know, it means that it is a decreasing function. Okay, so that is what happens when you have terminal potential difference, which is quite different to when you have voltage versus current. And then the last graph that I want to look at okay, is what if you have 1 over your current, okay, and you also have resistance. Okay, so 1 over current versus resistance. There, in this scenario, you will have a linear, positively linear function. All right, and again, we're going to just look at our EMF formula. Okay, remember EMF, if we write it in terms of current and resistance, that would be the external resistance plus the internal resistance. Okay, now, what if I decided then to write this function in terms of 1 over I? Okay, so basically I would divide by I both sides, okay? And then I have EMF over I. All right, and that's equal to external resistance plus internal resistance. And what if I divide it by EMF? If I divide by EMF, I would have 1 over I, which is equal to 1 over EMF multiplied by external resistance plus internal resistance. Okay, and if you want to multiply it in just to remove the brackets, so you'll have external resistance over EMF plus internal resistance over EMF. All right, getting back to y is equal to mx plus c. So our graph, our x is r, okay? Let me actually put it like this. Let me simplify it. Well, I don't know if I'm really going to simplify it, but it's 1 over EMF plus r times 1 over EMF. Okay, but yeah, anyway, if I'm going to write it in terms of y is equal to mx plus c, remember your x in this case would be your big R, and your y would be 1 over I. So you have a y, and that's x maybe let me put the R this side. Change things up a bit. Okay, so I would have X. So basically this would be my gradient. Okay, y is equal to mx plus b. And I hope you see that. So the gradient of this graph, okay, the gradient would be 1 over E and F. Okay, that's your gradient. And then what would be your y-intercept? Your y-intercept would be R over E and F. Okay, so yeah, I just wanted to introduce those first before we start with our question 8 there from the Eastern Cape during the 2021 exam. Okay, so we're going to just take a short break and come back. So let's start with the first question. Well, it's not question 1, but I just tried to look through past papers to see if I can get questions with graphs in it. Okay, but anyway, let's read what the scenario is. So we have a group of grade 12 learners wanting to determine an efficient conductor which can be used as the heating coil for a kettle that they are constructing for their Eskom Expo project. All right, and I am hoping that you guys will be the generation that will help us with our load shedding problems, right? So they connected each of the 3 conductors, A, B, and C, in a circuit and measured the current passing through the conductor and the potential difference across the conductors. Their results are shown on the graph below. So we have current versus potential difference, and I hope that you remember that if you have current versus potential difference, the gradient for it would be 1 over R, okay? Because it is your delta Y over your your delta I. Yes, it is delta Y, but in this case, Y is I. Delta I over delta V. Okay, so it's 1 over R. So, yeah, basically, those are the gradients for A, B, and C, which is simply 1 over resistance. So now let's start with 8.1.1. It says name any 2 variables that must be kept constant for a fair investigation. You know that if you're conducting an experiment or an investigation, you need to have constant variables, all right, or else it will not be a fair investigation. And in this case, I would say temperature is one of them, okay? Make sure that the temperature is constant, like for example, room temperature. All right. And then when it comes to, this conductor, I would say that the length of the conductor at least should be the same. Okay. So temperature, I would say maybe around room temperature or whatever the temperature is, just make sure you keep it constant. And then we could say the length of the conductor, okay, because you don't want to deal with a short conductor and then a long conductor, because that does play a role in terms of the longer the conductor might be, might change things. So the length of the conductor as well, at least keep it the same. Even the thickness of the conductor, okay, and the type of material of the conductor, please just keep it the same. And then going to 8.1.2, write on the physical quantity represented by the gradient of each graph. Okay, great. This is where we shine, and we know that the gradient here is 1 over R. Okay, because we've already covered that. And then 8.1.3, which one of the conductors is efficient enough to be used as a heating coil in a kettle? What do we want to see here? We want to see something with a high resistance, okay? Because we want to use that current as it passes through the conductor. Actually, these properties that we're mentioning here, they have to do more with resistance. And with resistance, we talk about the length, we talk about the thickness, we talk about the type of material, okay? So even here, when we talk about one of the conductors, which one of the conductors is efficient enough to be used as a heating coil in a kettle? Between A, B, and C, what do we want? We want something that has a high resistance, okay? And if you have a look at our graph, remember this is 1 over R. Our gradient is 1 over R, okay? So 1 over R means that if you have a higher current, remember this is change in current over change in potential difference, okay? So potential difference is actually, what do you call this? It's directly proportional to resistance, whereas current is inversely proportional to resistance, all right? So you can see with A, if I can make a mark here, I hope, or maybe not, but let's just take, let's just take this value here for A. So you can see the current is quite high, but the potential difference is low, okay? And over there, so if the potential difference is low, I know that my resistance is low. If I take the current over there, which gets quite smaller, I have an increase in potential difference, right? And if I were, actually, let me rather compare the same thing. Okay, let me choose the same current for all of them. And let's see how that would work out. Okay. So if I were to choose this current over there and then extend the other lines. Oh, okay. Just use a different color there and extend the lines. So extend B and then extend C. I tried. So for A, we can see that the potential difference is quite low. The lower the potential difference, the lower the resistance. If I go to B, still it's lower, but now when I come to C, let me just extend that again. So when I come to C, I have the highest potential difference there, all right? And that high potential difference will yield a high resistance. And if I have a high resistance, it means then the conductor would be efficient enough to be used as the heating coil in the kettle. Yeah, technology is failing me at the moment, but it's all good. You get the flow, right? There it is. Okay, cool. So which one are we choosing? We are choosing C. Okay, and why are we choosing C, conductor C? It is because it has the highest resistance. Okay, so because it has the highest resistance, and we know that the higher the resistance of the conductor, the more heat is produced in the conductor if the current is constant. Okay, so that is question 8. Now let's look at what Mpumalanga had. So it says learners conduct an investigation to verify Ohm's law. Okay, remember Ohm's law? And this is now question 9. Ohm's law says that resistance is voltage over current. Now, they vary the potential differences across a resistor and measure the corresponding current through the resistor. The data obtained is shown in the graph below. So we have current versus potential difference. We've covered that as well, right? And with current versus potential difference, we know that our gradient over here, just going to make that red. Again, our gradient over there would be equal to 1 over r. Let's just do this. Okay, 1. I give up. If we have current and we have potential difference, we know that our gradient would be 1 over r. Okay, cool. Now it says state Ohm's law in words. All right, so this is theory that you have to know. So basically, Ohm's law in words says the potential difference across the conductor is directly proportional to the current in the conductor, okay, at a constant temperature. All right, and then if we go to 9.2, it says the graph deviates from Ohm's law from point X. We can see that. So this portion here where you have a straight line, that's where Ohm's law is applicable. But here where you have a curved portion, Ohm's law is not applicable anymore. All right, and now it says 9.2.1, write down the potential difference at point X. So this is something you would have to read off from the graph. And if I look close, so this is like what? 1.1. Ah, my goodness. Okay, 1.1, 1.2, 1.3, 1.4, 1.5. Okay, so every two small blocks, that is 0.1. Okay, and I see this X is at the fourth block. So this is like 1,2. Okay, 1,2 volts. And then 9.2.2, write down the current at point X. Okay, these were like giveaway marks. You'll have to see here. So 2, 4, 6, 8, 10. So that is 5.2, more or less. So we have 5.2. Don't forget that times 10 to the power -2 amperes. Okay, that's the current. And then 9.2.3 says, give a reason why the resistor does not obey Ohm's law from point X. What could have happened at that point in time? Okay, I would say one of the reasons would be the temperature has increased. Okay, so if the temperature increase in temperature, that affects the resistance. So at the beginning, we had a constant temperature, all right? And all of a sudden now, the temperature is just increasing over the last portion. Okay, so I would do that. And even the resistance, because the steeper the graph is, the less the resistance, just like we saw here. Graph A had a very steep gradient, meaning the resistance was less, but the flatter the gradient is, it means there's an increase in resistance. And resistance also with temperature. If you increase temperature, resistance as well increases. So in this portion after X, the resistance could have increased, or it did increase. The temperature also could have been increased. And now we get to 9.3. When the potential difference is less than that at point X. Now we're looking at the portion with the straight line. It says calculate the gradient of the graph. Okay, so you can choose any 2 points. The gradient, which we know is actually 1 over r, is change in current over change in potential difference. And you can go and look and take any 2 points along that straight portion and work with them. Okay, so we already have the points at X. I would suggest that we use them, and also use which other point? You can use any other point. Okay, so if maybe we can go to 0. Okay, so let's see. We can then say 5 comma 2 times 10 to the power negative 2, and we subtract 0, which makes life way easy for us instead of trying to look for another point. And we know that the potential difference at that point, we did have a look, it's 1 comma 2 minus 0. And if we work that one out, okay, it's going to be 5 comma 2 times 10 to the negative 2 divided by 1 comma 2. And we get a gradient of 0,043. And what is the unit at that point? Well, because we have 1 over resistance, I don't know if if it would be safe for me to say 1 over ohm. Okay, but yeah, that's basically the resistance, the gradient at, yeah, the resistance. Oh, no, what am I calculating? Yeah, the gradient of the graph. That's basically the gradient of the graph, 0,043. Actually, because the gradient, I don't even think I need to use a unit, but it's fine. We can keep it there. So that's 9.3.1, and then 9.3.2, the resistance of the resistor. So we know that 1 over R is 0,043. Okay, I'll just put it like this. 0,043 divided by 1. So if I want resistance, I'll then say 1 over 0,043, which would then give me a value of 23,08 ohm. All right. And I believe that is that. So I'm just going to take a break before we get on to the 2018 paper. Welcome back, and we're going to have a look at question 9 of the March 2018 paper. Okay, so what do we have this time? Now there are 2 graphs below that show the relationship between current and potential difference for 2 different conductors. Okay, yeah, so far we've seen a whole lot of current versus potential difference, and you know by now that the gradient of the straight line would be 1 over resistance. Okay, so this would be current, and that's potential difference. Now it says for 9.1.1, state Ohm's law in words. We have already covered that, but just in case you have forgotten, basically it says the potential difference across the conductor is directly proportional to the current in the conductor at constant temperature. So constant temperature is quite important. All right, and then 9.1.2, it says which one of the 2 conductors, X or I, sorry, not I, but Y, X or Y is ohmic. Okay, for it to be ohmic, guys, it has to be a straight line. The moment it starts to curve, it means that the temperature is changing. Okay, the temperature is not constant anymore. So the one that shows an ohmic relationship is X. Okay, graph X. And why is graph X the one? Because it is the straight line passing through the origin, okay, and therefore the potential difference is directly proportional to current. Where you have a curve, it will not be directly proportional to current, and where you have a curve, it means that the temperature is changing. Okay, your resistance is busy changing. If it's getting flatter, your resistance is increasing, and that's something that we did refer to in the previous question. And that is that for that paper. So now the November 2018 paper, this is what we have. I'm just going to reduce the size. I hope you can see clearly. All right. And then it says, learners perform an experiment to determine the EMF and the internal resistance of a battery using the circuit below. Okay, so now we have EMF. All right, things are changing up a bit. So let us see then what we can do with that information. So the learners use the recorded readings of current and resistance together with the equation R, big R, external resistance, is equal to the EMF over I minus internal resistance to obtain the graph below. Okay, so we have resistance versus 1 over current. Okay, this is question 9. Okay, we have resistance over 1 over current. Okay, and then we have our gradient over there. All right, now let's see, what do the questions say? Okay, 9.1, which variable has to be kept constant in this experiment? Okay, what do you think? All right, in an ohmic relationship, we know that what needs to be kept constant would be temperature. I hope by now you are getting the drift. As soon as you start increasing temperature, your resistance will increase. You will not have a straight line. It'll tend to be more of a curve and blah, blah, blah. 9.2, refer to the graph. So 9.2.1, write down the value of the internal resistance of the cell. Okay, so now let's see. With our graph over here, if we were to use EMF being equal to your current, your external resistance plus your internal resistance, and we have seen that this graph is a bit jumbled up. We're going to divide by current and we're going to divide by EMF. So you're going to have 1 over I, which is equal to 1 over EMF times R, and 1 over EMF times the internal resistance. Okay, and we, in this case, okay, things have changed a bit. I think let's rather put it in terms of R. Actually, they've put it for us. So we have R, which is equal to EMF over I. Okay, so we just took the I this side, and then we subtract R. Okay, so if it is like this, I would then say R is 1 over I. No, actually, let's just say EMF times 1 over I minus R. And I hope you can see here that R is Y, 1 over I is X, so that should be M minus R. So there, at the y-intercept, you have your internal resistance, okay? And your gradient is equal to EMF. All right, I hope you see that clearly. So now let's get back to the question. It says calculate the EMF of the battery. What are they looking for? They're basically looking for the gradient in this case, okay? So EMF, I'm just going to take 2 points that are quite obvious. This is 9.2.2. No. Oh no, did I skip a question? Write down the value of the internal resistance of the cell. Oh, here I'm skipping things. Okay. 9.2.1, write down the value of the internal resistance of the cell. We're basically going to look at the y-intercept. And at the y-intercept, if I have -5 over there, -4, -3, -2, -1. So yeah, I'm going to get it to be -3. Okay, internal resistance. I'm expecting it to be a negative. Ne? It is on the negative side. What's going on here? There we go. So I'm expecting it to be on the negative side, okay? So, but I don't want to say it's -3 because if I substitute -3 here, it means now I have a positive. So I will then just use 3 ohms. Okay. Plus, in real life, we're not going to have a negative internal resistance. It would be positive. All right. So that is that. Now we can get to 9.2.2, which is the gradient. Calculate the EMF of the battery. That's your gradient. So here we're going to just choose 2 points along the graph and then see what we can do with it. All right. So, sorry about that. Which one is easy to read? Okay, I think I'm going to go with 1,5. Okay, 1,5 on the X, and then the Y is around, looks halfway. So 6, 7. Looks like 7.5. Okay, I'm gonna go with 7.5. And when you see the units, it's just okay, 7.5. And I'm gonna take it to 0. Okay, so where I have 0 on the X, I have -3 there. So minus 3. And then our EMF would be 7,5 plus 3. Remember, it has to be a positive gradient, not negative, whatever it is that you calculate at the end. And we get our EMF to be 7. And remember, EMF is measured in volts. Okay, so that is that. And okay, yeah, that's it with this question. Let's now go to the 2017 November paper. Let me just make this a bit smaller. I think by now you're getting the drift, right? We can stop this lesson here. But for those who want to continue, let's go along. So question 9 from 2017. It says learners investigated the relationship between potential difference and current. Okay, so in this case, potential difference over current will give you resistance. Not 1 over resistance, but basically resistance. Okay, and yeah, so a potential difference in current for the combination of 2 resistors, R1 and R2. In one experiment, resistor 1 and resistor 2 were connected in parallel. In a second experiment, resistor 1 and resistor 2 were connected in series. So the learners then plotted graph X, the results of one of the experiments, and graph Y, the results of the other experiment. Okay, so one is in series, the other is in parallel, and you have to then probably decide which one is which. Can you tell the difference? All right, let's start answering for 9.1. State Ohm's law in words. Okay, this question is just recurring. I'm not going to answer that. We have already covered it. 9.1.2, what physical quantity does the gradient of the potential difference versus current graph represent? We have spoken about it quite a number of times, and in this case, it would be resistance. Okay. 9.1.3, calculate the gradient of graph X. Okay, so resistance of graph X looks quite to be high. I would take this value here at 2. Okay, so delta Y over delta X, or rather delta V over delta I. So we have there 2 minus 0, and then I would be 0,5 minus 0. So the simplest to take 2 divided by a half, that would be 4. And we have ohms. Okay, so that was nice and easy. 9.1.4, determine the resistance of resistor 1. Okay, so we have 2 resistors, remember? Resistors in series and resistors in parallel. So we don't know which is which. But R1 and R2 are connected in parallel. And then in the second experiment, R1 and R2 are connected in series. Okay, so we're gonna probably gonna need two equations because we don't know what R1 or R2 is. All right, now let's say we're looking at the portion where they are connected in series. So if they're connected in series, we know that we're gonna add R1 and R2, and it's gonna give us for X 4 ohm. All right, because the gradient of the graph is your resistance. Okay, so 4 ohm, and then in parallel, remember we have 1 over our parallel connection, which is equal to 1 over R1 plus 1 over R2, and we can actually go and calculate the resistance here, Y, which would be the one in series. Sorry, in parallel. Okay, so in this case, the gradient there, let me go work out the parallel resistance. So the gradient, I would take 0,5 and 0,5 and just subtract 0. Okay, so I see that it's actually 1 ohm. All right, so that's my slight calculation, little calculation over there. So 1 over 1 is equal to 1 over R1 plus 1 over R2. So I have two formulas now, two equations rather. That's my first equation. My second equation, I'm just going to say R1 times R2, and I have R1 plus R2, okay, which is equal to 1. And if I just turn it around, I would have R1, R2 over R1 plus R2. And I can say for my first equation that R1, how many marks is this? 4 marks. I feel like I'm working too much. Okay, R1 is 4 minus R2. So I can go and substitute it there. 4 minus R2. Okay, and then we have R2. Again, 4 minus R2 plus R2 is equal to 1. So then minus that, okay, I can take the 4 to the other side, and I have 4R2 minus R2 squared. So R2 squared minus 4R2 plus 4 is equal to 0. So I have a quadratic formula. So you're going to go ahead and use the quadratic formula. I'm going to speed ahead. Okay, and not cheat, but just use a calculator that is quick for the sake of time. All right, so then I find that R2 is equal to 2 ohm. Yeah, so R2 is equal to 2 ohm. Now I can go get R1, and I'm going to use the first equation, which was the simplest. R1 plus R2 is 4. So basically, R1 is also equal to 2 ohm. And that's what they wanted. They want the resistance of R1. So there it is. It is 2 ohm. Okay. And are we done with this one? Yes, we are. Let's take another break and continue with questions. When are these questions finishing? Oh my word. Okay, we have 3 more. We're going to tackle those. We're going to tackle those 3 after the break. Welcome back to the last portion of this lesson. But like I said, I think by now you're getting the gist of it. So this is Eastern Cape 2022. That is the prelim. Okay, And let's see. So it says a battery, a learner sets up a circuit to determine the EMF and internal resistance of a battery. And then what do we have before us? We have external potential difference. So we have voltage versus current. This is interesting because we are used to, this is the external potential difference. But still, if we're looking at our voltage versus current, we're expecting this, right? Where our gradient is resistance because we have it as delta V over delta I, but now we're getting it to be the other way around. We have a negative gradient. Okay, let's have a look what's happening here. Now 8.1, define the term EMF of a battery. Okay, a different question this time. They're not asking us about Ohm's law. Okay, so with the EMF of the battery, it's basically the total energy per coulomb of charge that a battery can supply. Okay, and therefore you get that equation EMF is equal to your terminal potential difference plus your lost volts. Okay, if ever the switch is off, or the switch is open rather, in a circuit, what you're going to read is the EMF, the maximum V voltage in the graph, or rather in the circuit. So anyway, EMF of the battery is simply the total energy per coulomb of charge that a battery can supply. Okay, now it says use the graph to determine the EMF of the battery. Okay, so this makes sense then, that we're dealing with EMF and not exactly potential difference. Okay, so this is potential difference, but if you were to deal with EMF versus current, then yes, we're expecting something like that. But yeah, determine the EMF of the battery. No, that would be terminal potential difference, not EMF. And there we go. So what is the EMF of the battery? I hope you remembered that actually the y-intercept. Okay, let's just go back to those graphs. We have terminal potential difference. Okay, sorry, should be up there. Terminal potential difference over versus current, your y-intercept is actually the EMF. Okay, so yes, this is where we are. So your external, instead of using terminal potential difference, you could have just said V external plus V lost or V internal. Okay, but anyway, the y-intercept would be your EMF, and that's why it's just one mark. It's something they expect you to know, something that you can read off quite easily. So the EMF in this case would be 1,4 volts, 8.2.2. Calculate the internal resistance of the battery. Okay, going back to our graph, where was the internal resistance again? So yes, the internal resistance was our gradient. Okay, hope you remembered. So yeah, let's calculate the gradient. Okay, so internal resistance, it's our gradient, which is basically delta V external over delta I. All right, and we're going to choose the simplest values we can get. There's the 1,4 as well as 1,4 minus 1,2. Those are the simplest to read. And I, which is at the bottom, so 1,4, that would be 0. And then we have 2,5. Yeah, we have 2,5. All right, so 1,4 minus 1,2, and then we have negative 2,5, and you have an answer of 0,08 or negative 0,08, and that is basically that. Okay, but yeah, your internal resistance can't really be negative, so that is your gradient. Okay, let's just say gradient, and then your internal resistance is just going to be 0,08 ohm. And is that it? Yes, that's it. Short questions. Nice. So question 8. This is the 2020 prelim from the Eastern Cape. In an experiment to determine the EMF and internal resistance R of a battery, a group of learners connected the circuit diagram below. They recorded the ammeter and voltmeter readings. They repeated the experiment each time with a different resistance. All right, so we have 1 over I versus R. Okay, if they talk about EMF, we're going to refer to this graph over here, 1 over I versus R, where the y-intercept is internal resistance over EMF, and our gradient is 1 over EMF. Okay, so using that knowledge, let's see what questions can we answer here. All right, so it says 8.1. What is the independent variable for this experiment? So the independent variable, that's basically, if you want to cram, your y-axis is dependent on the x-axis. Okay, so your y-axis would be dependent variable, and then your x-axis would be the independent variable. So the independent variable is normally plotted on the x-axis, where it doesn't really need anything else to exist. The resistor is, you know, what it is. Okay, but 1 over I is dependent on the resistor. Okay, hence y-axis dependent, x-axis independent. Okay, so in this case, our independent variable would be the resistance. And 8.2, using the equation 1 over I. Okay, so they've put it there for us. And we have, I'm going to say 1 over EMF times R plus 1 over EMF. Oh, they were so kind to put it nicely for us. And if you can remember, this is Y. As you can see, it's on the y-axis. R is on the x-axis, so this is your gradient, and that is your y-intercept. Okay, so I hope that is clear. So 8.2.1, use the equation to calculate the EMF of the battery. All right, so if we're going to calculate the EMF of the battery, you can use the gradient because the gradient is 1 over EMF. Okay, so gradient, which is 1 over EMF, is equal to your delta 1 over I over your delta R. So let's go look for values that are simple to read off. Okay, let us see. I think I'm going to go with this value over here, or maybe 15. 15 seems to work out quite nice, I think. Okay. Okay, so 15. Let's start with 15. And then what is the y value for it? So 2, 4, 6, 8, 10, 2, 4, 6. So 2,6. 2,6 works nicely. And then we're going to subtract this last value over here. So I will have 0,2. And then we have 0. Okay. Now let's work that out. So 2,6 minus 0,2 or over 1 5. It's 15. Okay, not 1,5. Okay, 1, 5, and we get 0,16. Okay, that is 1 over EMF. They asked for the EMF of the battery. So this is 1 over EMF. So now in order to get EMF, I'm going to say 1 divided by 0,16. And that is 6,25 volts. All right, so that's a nice 4 marks. And 8.2.2. Internal resistance of the battery. Okay, let's see. So internal resistance, I will get it there as the y-intercept. Okay, so y-intercept, which is C, is basically R over EMF. Yes, and that is equal to, if we check over there, the y-intercept is at 0,2. Okay, so R will be equal to 0,2 times the EMF, and the EMF, we calculated it previously as 6,25. So our internal resistance is 1,25. Great. And now 8.3. Wow, this was a lot of marks. This whole question, I'm expecting something short. Okay, no, we're not going to do this question actually. We're only focusing on questions that have to deal with the graphs. But anyway, we're here. We can skip it, but for those of y'all who are here, let's just see what we can do. So 8.3, in the circuit diagram below, the battery used in the above experiment is connected to 3 resistors and a toy car that is rated at 3 watts and 1,5 volts. Okay, so the switch is opened at the moment. Now, how about we close the switch and calculate the reading on the ammeter? Okay, so how are we going to do that? Well, basically, 8,3,1, reading on the ammeter. So we had the EMF from the previous question, right? Well, actually, no, where am I going so far? In your equations, you have an equation because watts, that's power, and voltage, and I. Okay, so power is actually equal to V times I. So we have 1,5 I, and the power is 3 watts. So your current is simply 3 divided by 1,5, which is 2 amperes. All right, we're almost there. 8.3.2. We need to calculate the resistance of resistor R. So we have our battery there, and we have an internal resistance. Remember, they said that the circuit diagram below, the battery used in the above experiment is connected. So our internal resistance would be the resistance from the from 8.1 and 8.2. Okay, so 8.22, we found that the internal resistance is 1,25 ohm. And then we have our resistor R. Okay, I'm just going to lump up those resistors in series. So this is our 3 ohm resistor. And then we have the toy car. It's going to say TC. And then we have our ammeter here that would measure 2 amperes. Okay, so we have our current there. Actually, let's just do it like this. Yes, so the current is flowing in that direction. Yeah, flowing in that direction. It's 2 amperes here. Then it divides, goes back to being 2 amperes up until. Okay, so how are we going to get resistor R? We already know the EMF of the cell. Okay, so we have our overall current, our external resistance, and our internal resistance. We have the internal resistance, we have the current, we have the EMF as well, which we calculated previously, didn't we? Yes, the EMF that we calculated, we got 6,25. Okay, so we have 6,25. Our current is 2. We don't know what the total external resistance is, but we know the total internal resistance, which is 1,25. Okay, great. Now we need another equation. So that, okay, no, we don't. We can just calculate what the external resistance is in this case, which is not this R, by the way. Let me just say R external so that we know exactly what we are talking about and we don't mix things. Now we think we are done. This is 6 marks. So the external resistance would be 6,25 divided by 2 minus 1,25. And what do we get? So 6,25 divided by 2 minus 1,25, which is 1,875 as our external resistance. Okay. Now let's get to what R is. So our external resistance is equal to the 1,2. No, this is the internal resistance. Let me put it like this before I get confused. It's equal to our resistors in parallel plus the toy car's resistance. Let's start with the toy car. I think that is simple to do. So already for the toy car, we know that the power is 3 watts, the voltage is 1,5, and then there's this equation where we have power being equal to V squared over resistance. Okay, therefore resistance is equal to V squared over power. I almost said velocity. The voltage is 1,5, potential difference, and then the power is 3. So our resistance at that point, no, I want to go to Internet Explorer, onto my calculator. So I have 1,5 squared divided by 3, which is 0,75. All right, and that is the resistance of the toy car. Okay, great. So we have one of the resistances. Now let's get to R parallel. So R parallel is 1 over 3 plus 1 over R. Okay, and that is basically 1 over R parallel. So we have 3R over 3 plus R. And therefore, I'm out of pages. Therefore, R parallel over 1 is equal to 3R over 3 plus R. Okay, now let's go back and work things out. I'm going to put a bubble around here. I have the external resistance is equal to the parallel resistor plus the toy car's resistance. Okay, and the external resistance is 1,875. The parallel resistance is 3R over 3 plus R, and the toy car's resistance is 0,75. We're going to do some mathematics gymnastics. So 1,875 minus 0,75, and that is 1,125, which is multiplied by 3 plus R, and that is equal to 3r. So now we have 1,125 multiplied by 3. It's 3,375 plus 1,125r, 3r. So we're going to take the 3 minus 1,125, and that is 1,875r, which is equal to 3,375. So r, finally, 3,375 divided by the 1. Yeah, but yeah, basically our r is 1,8 ohm. Okay, yeah, that is it. 1,8 ohm. We are done. Whoa, we're not done. That's just 8.3.2. Okay, finally, if the resistor R is removed from the circuit. So let's get here. If it's removed from the circuit, will the toy car be able to operate as rated? Let's see. So we remove resistor R. Okay, so now we have our 2 amperes flowing through here. So the voltage there would be 6 volts. And yeah, so resistor R is removed from the circuit. Will the toy car be able to operate as rated? And remember, our EMF is equal to 6,25. Yes. So this is 6,25 volt. And we said here the voltage is 1,5. Okay, and remember our EMF is our external voltage plus our internal or lost volts. Okay, which is equal to I big R plus I R. This EMF needs to be 6,25. Okay, or less, but it has to be 6,25. That's just a given. Okay, so our internal voltage would be 1,25 times 2, which is what? 2,5. Yeah, it's 2,5. And then our external resistance now would be 3 plus, what was the voltage there? 0,75, ne? So 3,75, 2 times 0, no, it is 3,75. So 2 times 3,75. That's a lot. It's like 7.5. So basically, we're calculating our, look at me doing ohms. We basically have 10 volts over here, and our EMF is rated at 6,25. Okay, so let's get back to the question again. If the resistor R is removed from the circuit, will the toy car be able to operate as rated? No, it will not. And why is that? That is because our internal resistance has increased. Okay, or it will increase. All right, and yeah, and we see then, I mean, our EMF has to be 6,25. All right, and if we keep our current, actually let's do it like this. If we have our EMF that we have to keep constant, and we have our current, which we already have is 2, okay, and now we have our external resistance has increased, or in this case now our internal resistance will increase. No, sorry, our internal resistance stays the same. It is what it is. It's 1,25 because of the EMF here. If the EMF is 6,25, our internal resistance stays 1,25. So the only thing that really changes here is our external resistance. So now our external resistance has clearly increased. We have seen that, okay? And since that is the case, yeah, the rating will not be the same anymore, because in order for the EMF to stay constant, then if our external resistance has increased, we need to then decrease the current, okay? And if we decrease the current, remember power is equal to V times I. So if we decrease the current, the power rating will then go down as well. So yeah, resistor R being removed, the car will not be able to operate as rated, because it's rated 3 watts, 1,5 volts. So that will not happen anymore. By us decreasing the current, you will not get that V of 1,5 anymore, or that power of 3 watts. All right. And this is where we ended. Thank you for tuning in. I really just wanted to focus on the graphs today. This question at the end here, I don't know why I didn't leave it out, but yeah, hopefully it'll help you as well prepare for your electric circuits. Okay, that's it from me.